Hi guys, welcome to my first video. I'm a PC hardware enthusiast and a code monkey by day. I wanted to do this video to inform and also to dispel some myths relating to graphics architectures. Now don't be offended by the mention of GCN-like in the title. Allow me to say that this is actually a good thing, as you will soon see. There's a few key changes in Pascal that separates it from Maxwell, and this gives Pascal features and abilities that are much more suited to modern games and VR. What's the common theme for modern games? Well, the majority are console ports. As you may know, all the current major consoles, as well as future consoles, use AMD's Graphics Core Next or GCN architecture. This means developers have to optimize the game engines to best utilize GCN, and this has some consequences for PC gaming. There's a great video series from Adore TV which covers this. He calls it AMD's master plan, and I suggest you watch it to understand the current and future implications. Back to the GPU hardware. I'll try to keep it as simple as possible, and what I will talk about is purely a subjective look at the architectures. One key technique to extract performance from any GPU is what's called an optimal warp or wavefront. Think of it like a packet of work or queue submitted to the GPU to distribute to the shaders. Each GPU architecture often have a wavefront containing an amount of work that is distributed in the most efficient manner. For GCN, this workgroup count is 64 per wavefront. Note that this number 64 is not a coincidence. A typical GCN GPU is composed of many compute units or CUs. Within a compute unit, there are 4 SIMs, each comprising of 16 streaming processors or shaders for a total of 64 per compute unit. Each CU has a scheduler which distributes the work to the shaders as a wavefront. If you queue up less than 64 work items per wavefront, some of the shaders will idle for that cycle, thus you are not extracting peak performance from the compute unit. As such, one of the common approach developers use for GCN is to ensure the game engine schedules 64 work items per wavefront. If your GPU has more shaders per compute unit, it wastes additional cycles or latency before all the shaders get the correct work items assigned to them. Depending on the game engine, the extra shaders may not even get work items assigned, and so the compute unit is effectively running suboptimal. In the Kepler architecture, each compute unit, which is called a streaming multiprocessor or SM, has 192 CUDA cores. In Maxwell, NVIDIA partitioned and loaded to 128 CUDA cores, and this results in an increased efficiency as the ratio of registers, cache, and scheduler per CUDA core has increased. With Pascal, NVIDIA has lowered this CUDA core per SM even further. Now each SM has only 64 CUDA cores. What this effectively means is that in modern games that are GCN optimized and work items are dispatched as groups of 64, Pascal will run as efficiently as possible without wasted cycles or potentially idle shaders. The second common feature of modern games are the increased usage of compute-based effects such as dynamic lighting, global illumination, ambient occlusion, dynamic particles, and realistic shadows. It's a trend that will only grow as developers use more advanced effects in next-gen games, and it can be a major problem for Maxwell and Kepler. This problem is clearly illustrated by a recent example, DX12 Quantum Break, where the AMD 390 can be anywhere from 50 to 100% faster than the equivalent NVIDIA 970. Now this is a more extreme example, but there have been many recent modern games where GCN has punched above its weight. The reason why such a huge disparity exists is because Kepler and Maxwell has a penalty associated with switching its SM and CUDA cores from processing graphics to compute and vice versa. Sebi, a well-respected member at the tech forum Beyond 3D, explains it quite well. All modern GPUs are able to execute multiple shaders concurrently. However, on Intel and NVIDIA, the GPU is running either graphics or compute at a time. So in order to maximize the performance, you want to submit large batches of either graphics or compute to the queue at once, not alternating between both rapidly. You get a GPU stall, wait until idle, on each graphics and compute switch, unless you are AMD. NVIDIA also tells developers not to do this switch unless it's absolutely necessary, because this is still a heavyweight switch to make. This penalty is referred to as the slow context switch, and it occurs at each change in workloads. While in terms of the overall timing of a frame, this context switch takes a tiny fraction. However, rapid and frequent context switching results in a major performance drop-off. We can see this in finer detail by analyzing the GPU view results of a typical frame in Quantum Break. GPU View is a tool from Microsoft that enables developers to debug their game engines. It's quite clear that Remedy, the developers of Quantum Break, are heavily using compute queues and interleave it with graphics. They do this frequently too. As a result, it's like a kneecap shot to GPUs with a slow context switch. Note the saturation of the copy queue, a typical memory-related task that do not even utilize shaders. This relates to DirectX 12 async compute, which I will talk about in a different video. For now, just understand that as games use more compute effects, GPUs which have a slow context switch will suffer in performance as the latency penalties adds up to be significant. The good news is that Pascal has improved in this area compared to Maxwell. Pascal features fast graphics to compute context switching, a feature that's available in the earliest GCN architecture. This is actually the reason why it's commonly said that GCN is good at computing games. GPUs which support fast context switching can run compute-heavy games without a performance penalty. So, how do we know that Pascal supports fast context switching? Based on what NVIDIA have claimed, Pascal is capable because it supports what's called priority preemption. NVIDIA mentions in the Pascal white paper, note, the new Pascal compute preemption feature allows compute tasks running on the GPU to be interrupted at the instruction level granularity and the context swapped to the GPU RAM. This permits other applications to be swapped in and run, followed by the original task's context being swapped back in to continue execution where it left off. Now, hold on, we've heard this term somewhere before, right? Indeed, NVIDIA have claimed that Maxwell also supports priority preemption. They told VR developers that Maxwell was capable of having a queue on priority that will halt the current task in the GPU to switch to working on the priority task. To quote, it's a separate graphics context that takes over the entire GPU whenever work is submitted to it, preempting any other rendering that may already be taking place. In reality, this does not work, and NVIDIA was being generous with the truth. It turns out Maxwell, along with Kepler and Fermi, cannot actually perform preemption. The reason is quite simple, and NVIDIA actually explains it. All of our GPUs for the last several years do context switches at draw call boundaries. So when a GPU wants to switch context, it has to wait for the current draw call to finish first. True preemption is the ability to halt a draw call being processed anytime to switch to another work item, finish the new work item, and then resume the prior draw call. This is a feature that GCN already supports for a long time, and it's why AMD have claimed their GPUs offer a superior VR experience. Let's talk about VR. The single most important factor for VR is the user experience and how comfortable it is to immerse yourself in VR for longer periods of time, say half an hour or longer. To have a comfortable VR experience is essentially fooling the brain that what you are seeing is as close to reality as possible. For this, you need very high frame rates along with high resolution. However, there is another critical factor that is perhaps even more important than just having high frame rates. It is what folks in the VR industry refer to as motion to photon latency. What is it? Simply put, it is the latency between an action occurring and the result being displayed. This is how NVIDIA puts it. The standard VR pipeline from input in, when you move your head, to photons out, when you see the action occur in-game, is about 57 milliseconds. However, for a good VR experience, this latency should be under 20 milliseconds. It's not just NVIDIA who makes this claim. Oculus says the same thing, as we can see here from John Carmack at Oculus. 20 milliseconds or less will provide the minimum level of latency deemed acceptable. Interestingly, for Maxwell, NVIDIA was very honest and made this admission. Maxwell's best effort so far at motion to photon latency is 25 milliseconds, clearly above the recommended mark for a good VR experience. There's a few ways to lower this latency, and these are additive, working together to improve the experience. The most obvious is having a higher frame rate and better VR headsets. We're talking 144 Hz or above, the higher the better. The second method is what VR developers call latest data latch, where the GPU and the VR headset talk directly to each other, bypassing layers of OS and drivers. A third method is what Oculus and AMD calls asynchronous time warp. Async time warp reduces the latency by warping a near-finished frame by updating its field of view to the latest head position data. I.e., if you move your head, the last frame the GPU processed will be updated with your new head position data, and so the visual output is now aligned and correct. If this is not possible, the last frame will be displayed at the old field of view, and to the user this results in a time lag effect, where your brain already knows your head has moved, but your eyes see the previous position. This disconnect with what your eyes and your brain see can lead to major nausea. So async time warp sounds great, right? Well, yes and no. Both Oculus and AMD have this to say. While great in concept, the execution of the time warp task must be timed carefully in order to be useful. Ideally, it should happen as late as possible in a frame interval, allowing just enough time for it to be complete before the next display refresh. If it happens too early, then the additional head movement can occur before the display refresh, causing a noticeable lag. If it happens too late, then it may miss the refresh and allow a visible juddering to occur. So, how does async time warp ensure that it runs at the right time? The GPU must support true priority preemption, in that any current task can be halted mid-flight and the async time warp task is run instead. On Maxwell or Kepler, this simply cannot happen because it only does context switching at the end of a draw call, not while a draw call is mid-flight. This effectively means that most async time warp for these GPUs will occur too late as it gets stuck behind traffic. There is no coincidence if you read Oculus reviews. Many reviewers on Maxwell GPUs mention feeling uncomfortable to downright ill, so much so they had to remove the headset and take a long break. Obviously, this happens in some games more than others. Games with a lot of head motion will inflict nausea quicker. Of course, Pascal is not going to fix this issue completely, but is a good step at matching up to GCN, though it's still somewhat behind in this regards. GCN still retains an edge here because it supports true preemption along with true asynchronous compute. What this means for VR is that GCN doesn't need to halt its graphics rendering to perform the async time warp. The time warp can proceed alongside the graphics rendering, which continues to work on the next frame. If used correctly, this can result in a latency advantage for VR. Note that both Pascal and GCN are still a long way from a truly immersive VR experience. But just know that GPUs with true priority preemption, when compared to those which lack this feature, can offer a more comfortable VR experience and a longer play duration. In summary, when the Pascal 1080 and 1070 gets reviewed, some of you may feel that the performance gains in games compared to prior generations is not that great, especially for the price of the reference or Founders Edition cards. However, if what Nvidia claims about Pascal is true, it is a lot more future-proof compared to Maxwell, simply due to the nature of console ports and compute-heavy modern games. The small performance gap is expected to grow as time goes on, and I suspect we may see many more compute-based Nvidia GameWorks features. Importantly, if you are an avid VR enthusiast, Pascal will offer lower latency to provide a better VR experience when compared to older Nvidia GPUs. I'll end this video here. There's more to discuss in the coming videos. If you like what you've seen, please hit subscribe. Thanks.